In the question, we are observing 3 uniformly charged plates. First, we're asked to find the direction of the electric field between the plates. There's a different direction between the positive and negative plate here and the negative and positive plate here. The electric field flows away from positive charges and towards negative charges. So in this region, the electric field is in the plus x direction, and in this region is in the negative x direction. Next, we're asked, what methods would you use to calculate the change in potential from A to B and from B to A? First, we must understand that the change in potential is the negative integral of the dot product of the electric field and the change in the distance. In order to find the change in potential from A to B, we're saying that the path goes from here, starting at A, and ends here at B. VB minus VA. So in order to go from here to here, we use two path integrals in one equation, and we'll add them both together. So we're going from A to 0, which is this integral, and then we're going from 0 to B, which is this integral. And we consider this 0 because it's in the center, is our origin, which is our center plate. In order to find it from B to A, we'll be saying VA minus VB because A is the final destination and B is the initial location. So we're going from B to A, which is in our negative x direction. So we go from B to 0 and from 0 to A, and we'll add them both together. Now we're asked to find VB minus VA given certain values. So we're only looking at our x component since our y and z component are 0 for both our locations and in both of our electric fields. So once we plug everything in, we have the electric field in the region where A is 120 volts per meter, and the electric field in the region where B is negative 100 volts per meter. So since our integral is the negative electric field, we have a negative 240 volts here, and we have to add it to our change in potential. Our change in potential for our region of B, which would be 150 volts. So we have a negative 90 volts. Now we're asked to find VA minus VB under the same conditions. So VA minus VB is saying VB is our initial location and VA is our final. And we can look here. So we're going from here to here in the negative x direction. So we see here, once we plug everything in, we'll get a positive 90 volts. Well, one way to determine that if this is correct, we know that if the electric field is traveling in the opposite direction of our path, that the potential will be positive. So here we can see that this side is 240 volts and this side is 150 volts. So we're traveling in the opposite. We're traveling in this direction. So here our potential is, our electric field is opposing our path, and here is in the same direction. So this side would be positive and this side would be negative. And since this side has a greater magnitude, we can tell that our answer is correct because we have a positive value. Finally, we're asked, what is the minimum required energy of a proton to move from A to B, assuming there's a tiny hole for the proton to pass through and the kinetic energy is constant? Well, first we must use the equation work equals the kinetic energy plus the electric potential. We know that the electric potential is Q times potential. So if our kinetic energy stays the same, we can use 0 for that because there is no change, and we have the charge of a proton is 1.6 times 10 to the negative 19 coulombs, and we multiply that times our 90 from our part E of our equation where we found the potential, and we'll get 1.44 times 10 to the negative 17 joules.